there has been a slight change of plan. So basically, earlier today I tried testing the radio communication systems for the rocket, and it totally failed. I didn't manage to get farther than like 20 meters, so that's not a good sign. So what I'm going to do is I'm going to try to find another solution that we can use, be it with the same system, with another system, I don't know yet. So this episode we're going to be doing something different. As you can see on my screen, I have a file A1 radio protocol. That's what we're going to do today. We're going to be designing our radio protocol so we can define packets that can be sent over whatever communication system we will have, and that can be adapted, packets can be added, removed. So what I'm going to do is basically sort of time lapse of the entire process. So I hope you enjoy watching technical videos, because today is going to get really technical. So grab your snack and beverage of choice, sit back, relax, and enjoy the show. So this is what we got. We have a few sorts of packets. We have single packets, being 2 bytes in size, with a target, the target being either the ground or the rocket, and then a signal code, which is just like a designation, like it's this sort of signal. For example, the rocket can send to the ground, that's the target G, that's the ground, signal code 000, which is a ping request. And then the ground will respond with a packet targeting the rocket with signal code 001, which is pong. So that's ping pong, and that's the only thing the message, the single package will be used for. Then we have arguably the most complicated of the packets, the localization packet, which is 14 bytes in size, having a target, a signal code, and then positions being floats. These will be probably GPS coordinates. I haven't decided yet whether or not they're going to be absolute GPS coordinates or relative GPS coordinates, but we'll see about that. So an example packet like this is targeting the ground, because the ground doesn't need to send localization data to the rocket, it's the other way around. And it will send signal code 002, which is a position packet. And then I just plotted some numbers into this that are floats. So we have an example packet. Then we have a speed packet, having a target, a signal code, and either a speed or a delta speeds. And what these are is we have, once again, a target, which is going to be the ground most of the time. Then a signal code, which is once again 1 byte. And then a speed or a delta speed. So I'm once again going to put this in parentheses. Like this, because it's optional. It can also be absolute speed. And that's what you see here. We have target G signal code 003, which is SPD or speed. And I just plot 57 kilometers per hour. I don't know what it is in bald eagle wingspan, but you can use a calculator yourself. And then we have another one with signal code 004, which is the SPD or delta speed. And for example, the delta speed is 12, which means that our speed has increased by 12 kilometers per hour when compared to the last speed packet that has been received. Once again, you can calculate yourself what it is in bald eagle wingspans. I don't know how that system works. And then this is some sort of variable packets that we can use for sort of everything, which has a target, which is once again 1 byte, a signal code, which is 1 byte. But then we have a message length, which is a short, being 16-bit number, meaning that we can send messages up to 65,000 bytes in length. And then we have a message which is sort of, it's a byte pointer, with the length of the pointer being the message length. But I didn't know how to describe it in this sort of language to explain it, so I just took a byte pointer. And you can also see it here, target 1 byte, signal code 1 byte, message length 2 bytes, or short. And then the actual message is X bytes, depends on message length. So I think that sort of explains itself. And an example packet of this, target the rocket, with signal code 127, or signed byte limit. And within parentheses, we have gen or generic. It can be anything. Message length is arbitrary. And the message is, in this case, hello world. So in this case, the actual message length would be 13, because we have 13 characters, but it can of course be anything. It just, the length of the message has to match the length of message length, because otherwise we will have corrupted data, because it will try to read data that either doesn't exist, or it will skip over data that has been transmitted but is not going to be processed. So that's how the entire system works. It's maybe a bit confusing right now, but when we get to actually implementing this, I think it's going to be quite clear. But yeah, we'll figure that out soon. It's just, this is a bit of more comfortable territory for me, because I am no engineer, I don't know any physics, I don't have any experience actually building stuff, but I am a software developer, so this feels way closer to home. So for me, this is quite clear, but it may be not as clear as it should be to others. But that's not really a problem, because when we actually get to launching this thing, it probably doesn't really matter what's behind the scenes, it has to work. That's the only requirement we have, honestly. And we're going to be making sure that it actually works. So that's going to be this. And next phase will of course be implementing it. But because we have radio issues at this moment, that's also the reason why we don't have the comms tests. Yeah, we can't really test it right now or implement it, because we don't have a foundation. So I'm just going to leave this lying around, and we'll come back to this in a later episode. I know this episode has been a bit confusing and monotonic. We haven't done a lot, but I'm hoping to change that in the next episodes, or the next couple of episodes. So if you enjoyed, consider liking, subscribing, leaving a comment, all that good things. And I will see you guys next time. See ya!